All right, guys, we're on G2, thin lenses and what they are and how they work. Now, there are two main types of lenses that we are going to deal with. A double concave, which means that it bubbles outwards on both sides. And there's kind of the center of the lens. We'll get to why the center of the lens is important later. I guess you'll just see that. That's a double concave, or that's a double convex. Excuse me if I said concave a moment ago. It's double convex lens, and so we'll just refer to it as a convex lens, since we're not ever going to deal with single concave or single convex. Concave looks like this. Double concave would be kind of caving in on each side. So convex, bubbling out, and then concave, caving in on both sides. Okay, so two types of thin lenses. I'll get to the importance of why they have to be thin here in a moment. One other thing that I want to go ahead and set you up on is we are going to use ray diagrams to be able to sketch out where an image should appear if we have an object in front of the thin lens. So kind of the idea with these ray diagrams is you will have your principal axis. Okay, your principal axis. Your principal axis runs through the very center of your lens. Runs through the very center of your lens there. So equal parts on top and on the bottom for the lens. That's your principal axis. You have focal point, and you also have the exact same focal point, equal distance on the other side. So I need to figure out how far it is there, and it's the same over there. So this distance right here, this distance right there should be the same distance to over there. Sometimes you'll hear them called F and F prime, like focal point 1, focal point 2. Sometimes you'll hear F1, F2. It doesn't really matter. You have focal point on the object side, which this is normally the object side. Over here, you have some person or image of some way, shape, form, or whatever. You have something over here, whether it's a person, a car, or whatever. Then you have your lens, and then on the other side, you're going to end up having the image that's formed because of the lens. All right, so then down here we have image, and you'll see why I just drew that upside down a little bit bigger later on. Anyway, so those are the main things. I have the lens, the center of the lens, the focal points, object side, and over here the image side. Make sure that's a there. Okay, now that's the basic idea. Now, moving on. I'm not going to go through a full derivation here using Snell's law. I just want to kind of show you what's happening with lenses in general. So let's go back to our double convex lens, and let me make it a lot bigger here to where we can really see what's going on. Okay, now let's say a light ray comes in and enters the lens something like this, hits the lens. Now, remember, lenses are generally made of glass, so that would be N equals 1.5 for the lens. Now, outside you have air, right? So on both sides you have N equals 1, on the other side N equals 1, on the inside N equals 1.5. The thing you have to realize here, though, is this is a curved surface of glass, not a flat surface. And so the angle that a light ray hits at will be different depending upon where it hits on the lens. For example, down here, whenever it hits on the lens, let's try to find a perpendicular here. Something about like that looks pretty perpendicular. Okay, something about like this. It's pretty perpendicular. That means theta 1 is this angle right here. That angle right there. Okay, there's theta 1. Whenever it goes into the glass, it will refract closer to the normal. So it's going to refract something like this. Theta 2 becomes even smaller. Sorry for it getting really tight and difficult to see. Okay, so it refracts and becomes even smaller. But notice the normal is tilted, right? And I even drew that here straight, so let me try to redraw this up top in a way that will be easier to see. So let's come up higher where there's a bigger normal, where it's even easier to see. And so let's say I have a light ray that comes in like this, it comes in straight here. There's theta 1, theta 2 would have to look something like that, right? So theta 2 shrinks down. I apologize for drawing here. But then we're on to the other side of the lens, and so now I have to find the normal. The normal's kind of going the other way over here, right? I'd have to use trig to get from this theta 2 to figure out what that theta is right there, and now I'm back in the air, and so it's going to refract away from the normal, and so it's going to come something like this, where, you know, let's call this beta 1 there, and, you know, beta 2 there. So beta 2 would grow away from the normal as we go back into the air. Okay, so that would be the idea with thin lenses. You have to do Snell's law twice and some trig in the middle. So I would do Snell's law here. First off, having to figure out what theta 1 is, because, you know, the normal isn't straight there, and so I'd have to do some, I'd actually have to use a little bit of calculus if you were told that. Then I need to do some trig here in the center of it to relate theta 2 to theta 1, and so I need to draw a right triangle and blah, blah, blah. And then once I had that, I had to figure out a normal again, right? And then I do Snell's law again to get what beta 2 is. Boy, that's just really, really complicated. The great part is, if the lens is really, really thin, and the thinner the better, prevents any problems, which we'll get to later. But if the lens is good and thin, we actually have some rules where we've used Snell's law, and we found these certain things occur that will allow us to figure out where an image is formed without having to use Snell's law in all these different places. Here's what I mean by that. Let's give ourselves principal axis. And right now, I only want to deal with convex lenses. Okay, we're going to deal with concave next. But right now, let's deal with convex lenses. And you want to draw the center of the lens. That's where all these rules are going to reference. Okay, that's where all these rules are going to reference. Let's give ourselves a focal point. And the same exact distance for the focal point on the image side. By the way, the focal point, just as a concept here, and I'll point this out, with statement number 2 down here in convex rules, a ray that comes in parallel with the focal point. That is the definition of the focal point. So in other words, if I had all this, if I had a bunch of light coming in parallel to the principal axis like this, all of it will focus at the focal point, like this, right there. Okay, that's the idea of the focal point. It's where all the light focuses. Guys, you're probably familiar with this idea more than girls. A few of you girls might have done this. I think we might have talked about going out and burning ants at some point in time. But you know, you gotta you take a magnifying glass out, which is a double convex lens, and the idea is the sun's rays. The sun's so far away that the rays are coming in pretty much parallel, and so you get the distance to the ground lined up with the focal length, right, where the focal point is. So the focal length away, this distance right here, that's how far you'd want to position a magnifying glass above the ant. That way the focal point is right on the ant. It takes all the sun's energy that's entering the magnifying glass and brings it to a nice little point that then burns the ant. I don't endorse hurting animals, but if it's fire ant, feel free. Anyway. Let's get rid of that, and let's come back to this idea here. Now, let's set up for ourselves an image, or excuse me, an object over here. So I'm just going to make it, a little stick figure. You know how great I am at drawing. So a little stick figure here, and using some very simple rules, I can figure out where the image is going to form without ever having to use Snell's law. These rules down here. Rule number 1. A ray that passes through the center of the lens will continue straight through. In other words, let's talk about the top of his head here. a ray that goes right through the center of the lens, right here through the heart of it all, will continue as if it was completely unaffected. If you're thinking Snell's law here, what would have happened is it will refract in the center of it will refract whenever it enters into the lens, the ray will, but then will refract as it exits the lens in such a manner that it counteracts completely what happened before it. This, by the way, is also why the lens must be thin. If the lens is too thick, then there's a change in distance where it comes in and goes out, and completely messes this rule up. This is just one example of why the lens has to be thick. So there's rule number one: a ray that goes to the center of the lens keeps on going straight. Rule number two: a ray that comes in parallel will refract through the focal point. That one we've already talked about, right? Comes out parallel. This is rule number two. Will refract through the focal point. So something like that, excuse my curve. Whenever you're doing this, if you're doing this only by itself, which we're not going to be, we're going to be doing math later on. Whenever you're doing this, you need to be able to use straight edges to make sure things are really, really good. Anyway, rule number three, a ray that passes through the focal point will refract parallel. So a ray that goes through the focal point. Now, sometimes our lenses aren't drawn big enough, and that's okay if our lenses aren't drawn big enough, but a ray that goes through the focal point will refract parallel. Now we can already see that mine aren't lined up perfectly. Everything had hit at the exact same spot, which just means I didn't draw everything outright. Either the focal lengths that I have aren't the same distance whenever I was sketching this thing, or my lines aren't straight, which obviously they aren't, or some other problem. But what we're finding here is somewhere in this location right here would be the top of a person's head. Okay? Top of a person's head. Now, another little trick for you here. Thankfully for us, anything that is already on the principal axis will remain on the principal axis. Anything that's already on the principal axis will remain on the principal axis. And this person's feet are on the principal axis. The head is down below, the feet are on, so the feet must remain on the principal axis, which means I got this going on. Kind of the beauty of this idea that I'm just giving you right here, and let me put it into words, you only have to figure out the locations of 2 points of an object in relation to the image. All I have to do is figure out where the head of the object is going to be located image-wise, and the feet of the object is going to be located image-wise. And then I can fill in the rest, right? I already see what the object is. I can draw in what the rest is going to be. It's going to fill up the space in a proportional manner if this is a good thin lens. So I did the rules for the head, right? And figured out where the head was, and then whatever's on the principal axis will remain on the principal axis, right? So this would be an upside down, real, and it looks like it's a little bit bigger, magnified, blown up a little bit larger image. I'll get that. Let's get to that right now. Types of images. You have a few choices for types of images, okay, to describe what's going on. Is the object real or virtual? Is the object real or virtual? Is it inverted or right side up? Is it inverted or right side up? So here's your first thing, here's your second thing, third thing. Bigger or smaller? Bigger or smaller? Okay, so talk to me about, did it get bigger or did it shrink down because of the lens? So whenever I'm trying to describe an image, like up here, I'd follow my rules, and then I'd be able to say, okay, this image is real. This image is inverted, and this image is larger, magnified. Now, let me talk about, I think the inverted part, upside down, obviously, and the larger part, I mean, look at the heights here, you know. Let's use HO for height of object, and HI for height of image. I mean, look at the difference in the heights. I mean, obviously it's bigger, and obviously it's upside down. Now, let me talk about real versus virtual. Real occurs whenever all the light rays intersect. So here they're actually really intersecting at a location. Okay. Virtual happens whenever you have to trace things back. So let me do an example of that here really fast. So I'm going to set up myself a principal axis with a convex lens here. Give myself a couple of focal points. Right, same distance on the other side. Once again, I'm just measuring this out with my hands. It's not very precise. I'm just trying to show the rules. It'd be better if it was It'd be better if it was more precise. And let's stick an object inside the focal point just to see what happens. All right, let me follow my rules here. So let's scroll back up to look at them again. Rays that pass through the center of the lens will continue going straight through. So let's come down here. Notice the feet are on the principal axis. They'll stay on the principal axis. Means I just need to go ahead. So rays that go through the center will just keep on going. Okay, that's rule number 1. Rule number 2. Ray that comes in parallel will refract through the focal point. So ray that goes in parallel to the principal axis will refract through the focal point. Okay, I'm starting to see a problem. I think you'll pick up on this here in a moment. And a ray that passes through the focal point will refract parallel. Now, I have kind of an issue, right? I need to go through this focal point to make it come out parallel, but he's on the inside of it. Here's how this works. Make it as if it did come from the focal point. In other words, as if the ray came from the focal point. And obviously my lens wasn't tall enough in the way I drew it, so let me extend it upwards a little bit. A ray that would have gone through that focal point, it's as if it came from it, will refract out parallel. Now I got a big issue. Those rays diverge, meaning they will never, ever, ever intersect. Here's what you got to do. Trace them backwards, because this is actually how the eye works. So tracing all of these rays backwards, where they intersect is where the eye will see the image over here, right? That's where the top of the head would be. Where they all intersect is where the top of the head would be. And once again, feet on the principal axis, they'll stay on the principal axis. The eye actually, whenever light diverges and goes and it's separating away, the eye traces, I guess it would be the brain, traces where those light rays must have come from to figure out where the object is trying to see is. That's actually how real objects work. When you think about it, light hits something and then bounces off and radiates outwards. The light is diverging. It's going, it's separating out, generally in a spherical manner, but in more of a manner of whatever the shape of the object is. But the light rays are always diverging. You have to the eye and the brain traces that back to find where it is. So whenever the eye and the brain has diverging rays, it traces back. This would be a upright, virtual, magnified, bigger, right, image. Okay? And that works whether you're upside down, right side up. If the feet are not on the principal axis, you have to do the feet also to figure out where that's going to be. And we'll do examples like that in class tomorrow. Now, let me talk about concave really fast. Concave lenses work almost the exact same way. So let's give ourselves a principal axis here and a nice big concave lens. Okay. Here's the center of it. Let's give ourselves focal points, right? Okay, there we are. And let's give ourselves a little image. All right, a little closer. Now, the rules are almost the same, except the focal points are flipped. That is, which focal point you use for each rule is backwards. Convex almost feels natural. Concave feels backwards. Rays that pass through, here I am on number 1, rays that pass through the center of the lens will continue straight through. And that is the only thing that will always be the same. So let's draw a ray going straight through. it's going to keep on going. Number one. Number two, a ray that comes in parallel will refract away, and that should be not form, but from the first focal point. So a ray that comes out parallel will refract away from the first focal point over here, not down through the second, okay? But refract away from the first one. So here I am, I'm going to kind of trace this up and over. It's going to refract like that, away from it. That's actually a little too steep. Let's see if we can fix that here. Because trying to draw these accurately, it is important. Eventually, it won't matter too much because we're going to be doing math, but the drawings are the drawings allow us to check our answer. So that's why it's important to be able to get these. We'll get to that here later on. But anyway, 3. Rays that would have gone from the second focal point. So it's almost like I'm aiming for the second focal point. In fact, it's not like I'm almost aiming. I am aiming. In other words, if it could have, it would have gone through the second focal point. You see what I'm saying here? I'm aiming for it. Okay, let me erase my dots here. Okay. A ray that would have gone through the second focal point, if it could have, the lens wasn't in its way, will refract parallel. Parallel to the principal axis. All right, once again, I got a problem. The rays are diverging, right? Which means I need to trace them backwards. So, tracing the red one backwards, well, it's all on the same line. Tracing this guy backwards, it's something like this, and tracing him backwards, something like this, right? And by the way, you're always tracing the refracted rays back, not the initial ones. You always trace the refracted rays back. So that's giving me an object that is something like here, right? That's where the head is, wherever all those rays intersected. The people are already on the principal axis, so they stay there. This would be an imaginary image, or a virtual image, right? I don't know why it's already scratched out image. Oh well. A virtual image, right? Because you have to trace it back. The eye is tracing it back to find where it is. It's not the light rays actually intersecting, causing an image to form. It's your brain tracing the diverging rays back and making up an image where it should have been if these light rays that were refracted are traced back to where an object logically would have been placed. So this is a virtual image, not a real image, not real rays intersecting. It is upright and it is smaller. Virtual, upright, small. Let's do that again. And you can use that again, another example problem. Let's just put the image inside, put the object inside the focal point, because as you saw with convex lenses, there was a big difference whenever we did, right? I mean, if it was outside the focal point, we got a real inverted, larger image, right? And whenever it was inside the focal point, we got a virtual, upright, larger image. So big difference here. So let's give myself a little bit of room to work with here when dealing with my focal points. And so now let's give myself an image, say somewhere like that. Okay. All right, following the feet are on the principal axis, don't have to worry about that. Ray that goes through the center keeps on going. A ray that comes, let me label these guys. A ray that comes in parallel will refract away from the first focal point. So a ray that comes in parallel will refract away from the first focal point. Here's F1, so it will refract in a manner that takes it away. So I'm having to draw a dashed line to actually see what angle it's going to come at. So I'll start at F1, hitting this spot right here. Okay, starting at F1, hitting that spot, and then continuing to get it. So it's going to refract away. 3 rays that would have gone through the second focal point. So it's like I'm aiming for that focal point over there. So if I let it keep going, if I drew this correctly, it should go through. Okay, that's pretty good. Will refract parallel. So in reality, it refracts that. Okay. Once again, the rays diverge. That means I need to trace them backwards. Okay. So tracing everything backwards gives me an intersection right here. So there would be my image. That once again would be a virtual, upright, smaller image. For convex lens, if it's outside, just kind of rules of thumb here, if it's outside the focal point, this is convex. Now, if it's outside the focal point, you should always get a real upside down image, almost always bigger. If it's inside the focal point for a convex lens, you should get a upright, virtual, or imaginary, whichever way you like to call it, larger image. All right, so outside focal point, you're going to get something that is imaginary or virtual and upside down. Those two things almost always go together. Inside focal point, you'll get, did I say imaginary previously? Excuse me on that. If it's outside the focal point, you'll get a real upside down image. Those two things almost always go together. If it's inside the focal point for a convex lens, you'll almost always get, not almost, you will always get a upright imaginary image. Those two things go together. And with convex lenses, it's trying to make things bigger. Concave lenses like this one give the exact same behavior no matter where you are. Give the exact same behavior no matter where you are. Now the relative size changes, and we can discover that later on. But it will always give you a virtual or imaginary because you're having to trace the rays back. Concave lenses always diverge light. So concave lenses will always give you a virtual or imaginary image. It's always going to be upright. It will always be smaller. Okay. Whenever light rays diverge, expect it to be virtual. Okay. And with concave lenses, they will always diverge no matter where you're at. Convex lenses, there's only one case where the light rays diverge whenever you're inside the focal point. Another difference between them: convex makes objects bigger. Concave makes objects smaller. All right, that's it for this lecture. I'm sorry it kept going. I had a lot of content to cover. Make sure you have notes over this for tomorrow, and we'll get a little bit of work done.